But we're here to talk about what some people like to call the nexus, which I think is just fantastic. It's kind of like the Matrix or something. The energy-water nexus in particular. And I'm going to try to set the stage for that a little bit, and then I'm going to turn it over to my excellent panel of experts who are from a diverse array of industries that must deal with water. And I guess government doesn't count as an industry, but maybe we'll treat it as one on this panel. So, a factoid for you. Each day, the oil and gas industry uses 2.5 billion gallons of water. That's each day. And literally, all of that is lost. It's either lost in the process of fracturing wells or lost when it flows back down a disposal well. That's 2.5 billion gallons of water a day. And as we will soon find out, that's just a small fraction compared to what agriculture uses. U.S. agriculture is the big user of water. More than 80% of water goes to agriculture. So we're going to talk a little bit about how we might apply technology to address some of these challenges, particularly as we head into what might be a very water-constrained future due to continuing growth in use, but also climate change, things of that nature. You get a low snowpack in the west, and suddenly things get a little hairy, both for agriculture and all us city folks who want to have drinking water. So, without further ado, I will turn it over to my panelists, who will each introduce themselves, and we'll start with agriculture. Take it away.
Thank you. My name's Dave Jessen. Last 3 years I've been CTO of Chromatin, which is an ag startup and a sorghum seed company based out of Chicago and Lubbock, Texas. Before that I'd been 11 years with Syngenta, and prior to that 12 years with Pioneer Hybrids. So I'm a plant breeder by training, so I'm a little bit more focused on probably the genetic aspects to improvement of water use, but I'll try to represent agriculture as well as I can. So you're absolutely right. The food, fiber, and fuel that we grow to support the 7 billion people uses 70 to 80% of the water in the world. And besides just the quantity of water use, as we were talking earlier, there's water quality issues associated with agriculture as well, primarily erosion and nutrient runoff. And so, I mean, it is both a quantity and quality challenge in how we utilize water in agriculture. And clearly increased pressure from urbanization and industrialization and climate change is going to push agriculture into a very competitive landscape for water use. In the U.S., as you mentioned, there's actually 3 states that use 25% of the water. And those tend to be where, what do you have? Agriculture as well, mixing with population. That'd be Florida, California, and Texas. So what is ag doing about that is a question that I've been asked to try to answer. And I think there's a couple of real aspects around it that I can get my head around. One is crop selection. The other is the management of that crop. And then also, I'd like to spend just a couple seconds on the genetic improvement. And all of those are playing a role to reduce the drought tolerance, increase the drought tolerance, and reduce the water use efficiency of agriculture. So first, crop selection. Corn requires between 20 and 31 inches of water to produce a crop each season. Okay, sorghum's about half to two-thirds of that use for a crop. You've got some things like cotton, which actually starts at a minimum of 28 inches and goes up to 51 inches. So, I mean, it starts at the tie end of corn and goes above that. Then you've got citrus between 35 and 47 inches of water each season. So clearly there's differences within the crop. And so a farmer can clearly make choices about which of those crops to grow, but those choices are more than just water. It's about economic return choice usually. And farm bill policy, subsidies, and crop insurance all play a very large factor in that crop selection choice. And the example I know, the last 2 years, 2012 and 2011 and 12, have been a severe drought in West Texas. And you know, most of the growers there were better off economically by planting cotton and getting a disaster payment than they were by planting sorghum and actually getting a crop off that field. And so there's something probably not quite right if we're really serious about helping agriculture do this, if we're really making it an economic incentive away from more water effective and efficient crops. Of course, I'm in sorghum business, so you've got to recognize I'm probably a little biased on that. But it was very frustrating to see that sometimes those choices were not about what's necessarily the best crop for that field, but how they were incentivized to grow certain crops. Management of the crop. There's been tremendous improvements through sensors, through data, through GPS, in understanding how to do irrigation. Irrigation scheduling is just one of those now they can monitor the stress on the crop. They can understand the differences in their soil types, even with probes. They've done the types of sophisticated weather data to help them time their irrigation so that actually you can utilize less water and improve yields at the same time, because it's a more effective or more for the plant and how that water is applied and when. And so it isn't necessarily a feast and famine, but they can actually provide a more steady water source for that crop. And so there's been some significant improvements in this that have seen, and a lot of those again are economic driven, as the cost of pumping water has gone up. Conservation measures start clearly kicking in and paying for it. There's also significant irrigation system improvements. We've moved from flood irrigation, which was using gravity and the easiest and the cheapest way to do it, to furrow irrigation, which is a little more refined, to now sprinkler irrigation, where basically the effectiveness of the water application as well as the efficiency for which you can apply and move, that has greatly increased, but that all comes at a much increased capital cost for a grower or a farmer. Genetic improvement. So a key target for plant breeders and biotechnologists has been improving either drought tolerance or water use efficiency in the crop. There's a lot of challenges to that. This is a very complex trait, drought tolerance, as well as it's always generally combined with other stresses, particularly heat stress, and often salinity or salt tolerance is required as well. And so all of those can quickly lead to challenges, because most of the plant is using water to cool itself. I mean, that's the primary use of that, and that's to allow it to do its physiological processes as comfortably and more effectively as possible, similar to the reason we all have air conditioners in the summer, and it's very different. We definitely function better at the right temperature zone, and so the plant's just trying to accomplish the same thing, and that's where most of the actual plant use is. So measuring how you can significantly change that genetically really raises the questions of how you impact the physiological processes in the plant and ultimately the yield that can be developed off that crop. So currently, in the last couple of years, corn seed companies are trialing and have actually introduced hybrids with improved drought tolerance, and drought avoidance is also a characteristic. You can think of drought avoidance as just saying, how do I get over until the next rainfall, whereas drought tolerance would actually be, growing, or water use efficiency would be growing with a more limited amount of water application. And so those can be very different ways to try to accomplish that. And some of the products coming out are really geared towards allowing that plant to manage short periods of water stress, and then others are more focused, I think, on how do you get the plant to be more efficient overall and how much water it takes to develop that crop. So there is a lot of focus on it. How well and how much impact these technologies will have in the real world of agriculture is still kind of yet to be seen. And I kind of would like to wrap up with just an awareness for agriculture. I mean, right now, many of you aware of the Ogallala Aquifer. I mean, this is a tremendous value. It's an underground reservoir of prehistoric water. And we've been tapping into that just like you could, tap into an oil field, right? And that has allowed the expansion of corn production into Kansas and western Nebraska and many areas where you couldn't before. When you fly over, if you don't live in the flyover parts, you see all those green circles, and that's all been allowed because of the Ogallala Aquifer. And it's shrinking, and it's an issue. And I'm encouraged when I see things like Kansas has initiated some self-imposed irrigation restrictions because they're in the argument, they're in the discussion about whose water is that? Is that today's generations or is that future generations' water? And how do we make those decisions about how to use that water? And so it's very complicated. It's very difficult to change. Water rights have huge impact on the value of land. I mean, that was driven home to me with we just have a little place in Montana, and we've got a water right that dates back to 1869 on that. And we wanted to change it because it's a use it or lose it right. If we aren't irrigating, after 10 years, we lose that water right forever. And so what we tried to do was put a temporary change in to say we want to leave the water in the stream, in the spring creek, for a fishery. But we don't want to lose the water right because at some point that would significantly reduce the value of our land. Needless to say, thousands of dollars later in application fees and consulting fees to navigate the process, it really drove home to me how huge an issue it is for somebody that's much larger, that has much more complex problem than even my little Spring Creek issue. So I think there's not a simple fix, but policy is obviously a big part of it, and I think we're going to hear some about that shortly.
That's right. It's easier to change photosynthesis maybe than a government bureaucracy. But Ben will talk about that. One of the more interesting ideas I've heard here at ARPA-E is a bid to change plant reflectance in order to cut down on that cooling need. But we can maybe get to that a little bit later. Next up is Ken Mortensen, who will be talking to us about the next biggest user of water, which is cooling power plants instead of, green plants.
Yeah, thanks very much. It's good to have a session here on resources and water in particular. My name is Ken Mortensen. I'm Manager of Research and Development for SPX Cooling Technologies. Our main brand is Marley, which is pretty widely used in the power business. We are in all aspects of cooling, evaporative, wet cooling type systems, dry cooling systems, as well as hybrid type cooling systems. One of the problems with, as we've talked about here a little bit already, the water problem is the diverse nature of the water problem. Agriculture, thermal power generation, and consumer level uses of water, which are very, very different, large differences in numbers of users, locations, etc. So that it's one of the things that makes this a difficult problem to attack. In thermal plants, the main water use is condenser cooling at the turbine. It's probably 75 to 80% of the water use on the site. The boiler feed and these other scrubbing systems use substantially less water. So it's a big use and it's big users. So it ends up being an item of discussion regardless of the magnitude of it relative to some other things.
It's what everybody looks at when they look at a power plant.
Right.
They think the power plant is the cooling plant.
You're taking all my water.
Yeah.
But in terms of water use, let's break it down a couple of different ways here. In terms of withdrawal, which would be once-through type cooling, there are a large number of plants in the United States that are still once-through cooling systems that draw water in, run it through the condenser, and run it back out. So they redeposit it. Essentially, it's a continuous loop. It's just a matter of the size of the water intake and outflow and where you put those intakes and outflows. In that sense, it's competitive with agriculture in terms of the quantities of water that we're talking about using. But when you look at consumption, when you look at actually evaporative portion of it, the numbers change pretty substantially. In terms of consumption, it's probably only around 3 to 5% of the total use, where agriculture is a much larger, the bulk of it. But even consumer activities are larger than thermal. Again, I think it has a lot to do with small number of locations and using very, very massive quantities of water at that location. There's a whole range of things you can do, from wet cooling all the way to 100% dry, which consumes no water. Wet cooling is used predominantly because it's the most efficient from a turbine condenser perspective and back pressure perspective. So really, if you have the water available, you're going to want to use it for plant efficiency reasons. And that's kind of another piece of the conservation question here. It's really a trade-off between water use and energy use, because as you go from 100% wet systems to 100% dry systems, you increase the parasitic energy by 10x, basically, in order to do the same job with a radiator type cooler that's closed versus an open type system. So you can't really do both. There are systems, hybrid systems, that are in the middle. That's where some of the things I'm working on are applicable. There are a couple of innovations that I've done projects on that address significant reductions. One is insertion of an air-to-air heat exchanger in the plenum section of a cooling tower. Currently returning about 20% of the annual water usage that is evaporated, bringing it back essentially into the cooling tower as clean condensed water. As a phase 2 development, I think we can probably bring that up to a higher number, 35 to 40% probably, which is a pretty significant number. We have a prototype that's been running 4 years currently. We have 2 commercial sales. We built one. We're building the second. Although I'll point out that they weren't purchased for water conservation reasons. They were purchased for abatement of plume reasons, which is taking away the visible fog that may be a safety concern, problem on roadways, problems at airports, those kinds of things. There has been some talk about doing the right thing for the wrong reason. It's a byproduct. Water conservation is a byproduct of that. But it remains to be seen to me whether purchases will actually take place in the thermal segment based on purely water conservation type basis. The other trend is water substitution, which is pretty widely used at this point, taking us from potable well or surface waters that are higher quality to sewage effluent type streams that are available in mass quantities and have not been retreated to the extent that the potable systems have. So that's a pretty big trend. It can be done generally with material substitutions in the system so that you don't have corrosion and scaling problems. But there are some things being done. I think it remains to be seen, again, what the long-term water and energy trade-off is going to be for this market. So thanks for that.
I believe that the nation's largest nuclear power plant out in Arizona runs on sewage.
Effluent. Yes, yes, it does.
Yeah. So it is possible, and it is being done. Now we're going to turn to a technology that, if we can get it to work, we won't have to worry about how much water ag or thermal power uses. It's desalinization or desalination, however you want to say it. And my good friend Carlos, who I know from back in the biofuels days, is going to tell us about the latest there.
Okay. Thanks very much. My name's Carlos Riva. I'm the president of Poseidon Resources, but my background is also in energy. I've, of course, in my career spent a lot of time in development of new energy resources and electric power, conventional electric power, and renewables. So I can attest to Ken's comments about the significance of water in development of those facilities. In fact, apart from fuel supply and maybe more than tying into transmission lines, the availability and quality of water is probably the single most important siting feature for new power generation development. I think that also my experience has been that the treatment of that water is one of the more complex engineering elements of water in a power facility. And by the way, I've bought several Marley cooling towers in my day.
Thank you.
But now I've actually focused exclusively on water. Poseidon is a development company that develops and builds water projects. We've done a number in the water treatment space, but today we're principally focused on new supply through ocean desalination. Our innovation, our approach, if you will, is to co-locate our facilities with power generators that are on the coast that use once-through cooling. So we take our feedstock stream from their cooling water and make use of their intake and discharge structures to minimize any environmental impacts. Just recently, at the end of last year, Christmas Eve in fact, we closed the financing on a very large commercial project in Carlsbad, California. This is a 50 million gallon per day facility, so it's utility scale. It'll be providing, when finished, close to 8% of the entire water supply for San Diego County. It'll be the largest desalination facility in the Americas, twice the size of the second largest. And so we think it's a big deal in terms of opening up the market for new types of supply of water. Clearly, a number of areas are constrained because of the lack of alternative resources, but desalination, what in California they call water from the west, I think has now been demonstrated to be a very viable solution to a chronic water shortage that they experience there. And we think that there's ample opportunity elsewhere, certainly other facilities in California, also in places like Florida and Texas where large-scale utility plants are potentially viable. In terms of desalinated water, though, I think there is concerns about expense and the like, but I think it's important to say a few words about the nature of our product, because water, it may be a very simple molecule, but it's a very complex commodity. And what we sell in providing desalinated water is not just the molecule. First of all, compared to other sources, it's a very high quality model. It's fully treated. So unlike water from a stream or a reservoir or the like, which needs further treatment, ours is already treated to potable grade. That's not a big issue, but it's an important feature. The other thing I think more important is that it has effectively an infinite feedstock, or feedstock, I guess, which is its source water coming from the ocean. And as such, we call it drought-proof. California and the water supplies of Southern California are very subject to drought, the effects of drought and potential curtailment from that. This sort of decouples the climate issues from the water supply. Also, from the standpoint of Southern California, they get their water from quite a long distance, passing through various other entities and agencies, and what they want is water that they can control, that's local, and this represents an important source. I think I don't know the exact number, but San Diego County's indigenous water supplies would probably only support about 1/10 of the actual population. So to have 8 to 10% coming locally is important part of the water security that they worry about. The environmental impacts are small, and they're also completely able to be mitigated through a variety of different means. In the case of our project in Carlsbad, we're restoring some 60 acres of wetlands to reconstitute habitat to account for the entrainment of marine life through the pumping. So we think that it's a very good option from an environmental standpoint, certainly better than drawing additional water from existing streams or building dams on rivers to have more surface water supply. other thing I'd mention is that there's a lot of technology which, over the course of the last decade, has driven down the cost of the desalinating the water, principally through membrane technologies and technologies for energy reuse. One of the critiques of desalination is it uses a lot of electricity, but that use has been coming down significantly through these innovations. And I think it's one of the important aspects of the potential for these facilities to further innovate, in that it's in the nature of these membranes and components to be continuously maintained and replaced. So a membrane lasts maybe 5 to 7 years, and in 5 to 7 years' time, you look at what's happening in the state of technology development in membranes, and you can start to incorporate over the life cycle of your facility new technology in a way that, for instance, you can't in a large generator. You buy a large generator, that's your technology for 40 years. The process technology of desalination is very amenable to adapting new technology over time, and it'll drive down, obviously, the electricity used and the ultimate cost of water. I think the other feature I'll say about it is that there's a strange habit in the water world to, when people talk about cost of water, they talk about the price of water today and the price of the first year of operation of your facility, without recognizing the fact that water rates, particularly in areas like California, have been rising very steeply. And what you really need to do is look at a life cycle cost. So in the case of desalination, the majority of our cost is capital cost, and the escalation of the water price over time is quite a bit less than the historic escalation of water price. So we believe on a life cycle basis that our water will be cheaper than the current water supplies. But you've got to look at it like most industries would, on a life cycle basis, not on what does it cost me today versus what I'm paying for my supplies, because it is an incremental supply. I think I'll say one other thing about the nature of our project and our approach, which is the other element of innovation, that we have developed our project, and it's our philosophy to do all our future projects as PPPs, or public-private partnerships. In our case in Carlsbad, it's with the San Diego Water Authority, which is the agency responsible for providing water to the entire county. They are a terrific agency that's highly competent, that could do this themselves. But they chose, for a variety of reasons, to partner with us. And the deal, if you will, is that we as the developer take the development risk, which is the slings and arrows of dealing with all of the state agencies, the environmental agencies, the public. We put together the construction and operating agreements and the financing jointly with them, but we arrange for the financing, and we take the construction risk, and we get paid for water that we produce. They, on the other hand, take the risk of the market, that there will be a market for the water that we produce for a 30-year period, at the end of which they'll own the plant. That arrangement has allowed us to use the credit capacity of the agency, which is investment grade, and able to sell investment grade bonds to the market, again lowering the overall cost of water, and that to the benefit of the consumer. So we think there's a lot of innovation here, and hopefully it's something that we can replicate in several other locations around the country.
Innovation in the business model. So I am encouraged, if I'm reading this tablet correctly, you guys have done your job and started sending in questions. The instructions for how to do that are up there. I can see that they're pouring in even as we speak. But now, without further ado, I'll turn it over to Ben, who will give us the deepest insights into what is the role of government in this space.
I'm Ben Grumbles. I'm president of U.S. Water Alliance, and I drink. I'm a user. I'm a recovering regulator, too.
Aren't we all?
I had the distinct honor of being the EPA administrator for water for the country 2003 through 2008. I also was the environmental commissioner in Arizona 2009 and 2010, and I very much can tell you, David, that partly out of necessity but also out of vision, the Palo Verde nuclear generating facilities use wastewater from 50 miles away from the cities in the Valley of the Sun. Mm-hmm. And it's a great story on water reuse and that saying that there is no such thing as wastewater, just wasted water. And when you're between a rock and a hard place, wastewater looks pretty good, mm-hmm. as long as it's safe and the public can accept its use. And so that's a little bit about the U.S. Water Alliance that I'm heading up. We are focused not just on governmental roles, but as an NGO, a nonprofit educational national group. We are focused on from the grassroots level, building a national vision for water, shifting some of the paradigms, go from water being invisible to invaluable, focusing on the worth of water. That is a lot about pricing, but it's also saying and having experts and thought leaders recognize that water is local, but it is beyond local. And that's not just the interstate nature of water, it's also, there are key issues, the energy-water nexus. There are key policies on water that really need to be revisited and rethought. And so one of the other big paradigm shifts we have is for this group, this national organization called U.S. Water Alliance, working with agriculture, working with energy, working with water and wastewater utilities around the country, is literally to change the paradigm on what wastewater utilities are. So tomorrow's, the utility of the future isn't simply a treat and discharge facility, it is a center of regeneration. The heat, the nutrients, the biosolids, finding productive use and reuse. And like Carlos, I truly believe that reuse is the wave of the future. So the topic for this panel discussion that we're going to get into, which is going to be great because we've got some really thoughtful and different perspectives on this. Essentially, the answer to the question, what is the role of government, from my perspective, it is to do what can't be done by the private sector or won't be done by the private sector in an acceptable time. And it's about standards, setting standards, finding that right, sometimes magical balance of technology and time. I was at an event celebrating the 40th anniversary of the Clean Air Act, and a very thoughtful industry leader stood up and said, technology can work miracles, but not on demand. And so whether you're talking about cooling water intake structures or being able to use technology so you get more crop per drop, it does take some time. And government sometimes has to be the one that's really forcing those shifts. But I can't think of a more important topic to talk about at this hour than water and its relationship to energy, which leads me to my last thoughtful saying, which is a Ben Franklin one that many of you, if you've been to water conferences, have heard, and that is, we know the worth of water when the well runs dry. Now, Franklin also said, beer is living proof God loves us and wants us to be happy. So I'm looking forward to being happy.
Beer, where agricultural water use and our individual water use collide.
The other saying that I've heard, because I do a lot of agriculture water policy, is from some friends in agriculture, and that is, don't criticize agriculture with your mouth full.
It's a good point. So let's actually, because a lot of these questions are related to agriculture, and in particular kind of the breeding, the enhanced breeding we know as genetic modification. If I can conflate a couple different questions, how practical are some of these traits like water use efficiency or salt tolerance in terms of being a strategy for reducing water use as compared to, irrigation improvements or what have you. And the other question is, how will, and maybe Ben or maybe not can address this, how will regulation affect kind of the feasibility of those being adopted at any kind of broad scale? And keep the questions coming. Come on, people.
I mean, the technology really has to focus on, as I mentioned, I spent a fair amount of time working with drought tolerance in corn, so I'm probably much more familiar with that than some of the other crops. Clearly, with the amount of acres that are available that corn is grown on, making small changes will have a significant impact. I think that's really encouraging. I would expect there needs to be, there will be improvement, whether it will turn, will we grow corn like we would cactus? That's not going to happen, right? I don't think we'll get those characteristics to merge into a productive enough corn crop. But a lot of the approaches, I mean, there is avoidance things. There's stomata, number of stomata on the plant, so for water exchange, and you can change those things. It's how it holds turgor. There's waxiness on the leaves. There's lots of factors that are traits that can be pursued. One of the challenges you kind of have is when every time you look at a complex trait with lots of components that can affect it, trying to overemphasize one or reduce another tends to kind of have this equalizing effect, and so you generally have to be focused on just getting your end result. And so some of the approaches I've seen taken are really that. We're not necessarily understanding exactly all of these characteristics, but like in the case of now with genetic markers, you can say, I can track enough that these plants with these chunks of DNA perform on average better under stress than these, and therefore that allows me to select for and improve that characteristic, even though I might not understand the mechanism that's occurring. So there's approaches going that way. There's also approaches where it's very targeted on, hey, this is the pathway we want to impact. We want to put a gene in that does X, and we see that effect. And I think both of those can work. But I know that the drought stress in a corn plant is very different to me than the drought stress in some other plants. I mean, how it's impacted at drought, at pollination is just abnormally hurtful to the production of that crop versus some of the other crops. And so there's, an avoidance window is probably much more effective in a corn plant than it might be in another one. I mean, rice water use efficiency is going to be huge if you can get to a point where, you can go back to dryland rice completely. That's going to have a large impact. So I don't know how to really answer that, other than I found that there isn't probably one solution that's going to impact everyone. It is crop specific, and it can be even environmentally combination with the crop.
Mm-hmm.
Yeah, if I
You're going to weigh in on ag. Go for it.
I was going to ask or comment. I'm from Kansas City, but I had heard statistics on this last round of drought in Kansas, and the performance was dramatically better in terms of crop saving under those circumstances. I don't have exact numbers, but in a practical sense, isn't this already happening in terms of seed and et cetera, in terms of genetically?
Well, so clearly, there's a couple things. So yes, the corn crops of today are dramatically better than they were even 1988, which was one of the worst droughts. If you ever look at the corn production, you see this huge drop in 88. That's when Yellowstone burned, that really hot, extremely dry, as bad as this year. Corn crops are tougher. I mean, there's been a lot of breeding bought into it. There's a lot of, and obviously that breeding and that testing and evaluation occurs in environments where it's dry as well. And so they're able to find the ones that are. And so one of the big improvements has been not just on the genetic side, but what we call on the phenotype side, or the phenotyping, which is actually running really good drought trials and running uniform and understanding and exactly controlling the irrigation that you're evaluating and breeding that crop under. And that has had, I think, some really strides forward. And then, believe it or not, just like all of us, when we get worn down and have a lot of stresses on us, we're much more susceptible to a stress. Things like insect resistance, less pressure from weeds that have come from genetically modified traits, give a healthier corn plant that has more ability to handle the stress that comes along. So you're absolutely right. I mean, the corn hybrids of the 30s, 40s, 50s would melt down compared to what the current ones do.
Mm-hmm. So since you followed my instructions and interacted as panelists, I will punish you by asking you the next question, which is, can you talk a little bit more about the trade-off as we move towards a more air-cooled, or if we move towards a more air-cooled system versus today's, very wet, cool systems?
Yeah, that trade-off, I would say, it's a steepening curve. As you go towards zero water use, your parasitic power goes up dramatically to 5, 7, 10 times the amount of fan energy put into a wet cooling system. I think in between there are probably value propositions that make sense. The 20% water savings category uses only about 33% to 50% more energy than the full wet system. So versus a 10x, that's fairly low energy input. There's also an increase on the capital side, which is significant, and that's why I've talked about whether these investments will be made or not. Mm-hmm. Kind of the question for me would be how much energy do you have to input to get to, say, a 40% level or more interesting level, and that may be where the sweet spot is. In the 30 to 50% range, makes sense to save the water, but if you have available water, you should probably use it for the worst type conditions because, design summer type conditions, really your plant capacity is pegged off that number, 100% of the year availability. So that's a pretty high stress point. You probably want to be as close to full water as you can at that point.
And I imagine that the cost of these is only going up because so are steel prices.
Yes, correct.
Carlos, since this is a technology audience, they have a lot of questions about desalination. But I guess I'll ask the most basic one here, which is, to what extent is your technology limited by the kind of simple thermodynamics of desalinization? Obviously, in the most simple form, you're boiling water and then recondensing it. And are there any technology breakthroughs on the horizon?
Yeah, I should clarify that our technology is.
I know it's not that.
It's reverse osmosis.
Yes.
So you basically set up a pressure gradient across a membrane that drives the clean water to one side and concentrates the brine on the other. I wasn't very good at thermodynamics in college, so I'll dodge the heart of your question. But I think what we see is that
they're going to get you afterwards.
There's still a lot of improvement to be had. It's unclear whether it's breakthrough improvement in terms of energy efficiency, but we know that people are continuing to innovate with membranes. And we, again, expect to be able to incorporate those throughout the life of the project into the project. There's also a lot of work in reuse of that energy gradient through various strategies to recapture energy and use that to pressurize additional water. And again, these are smaller improvements, and in that vein as well, there are a whole series of control and technique related to how you actually do the maintenance. One way it's been described to me is because these filters are in line and there's value in changing them out. It's the same equivalent or essentially similar to when you rotate the tires on your car. You get overall better utilization of them rather than just throwing them out, when some get overused. So there's a lot of small things that that are working to drive down the cost of energy. The other thing, and again, it's interesting from our perspective, because we are a private entity that's looking to make a profit. Our contract incentives are always to find ways to reduce the utilization of energy over the life cycle of the project. That's really one of the few upsides that we, as the private owner, have, and it's a very important thing to us. So we're going to be constantly looking for those new technologies to try them out in our facility and see if we can bring that down.
Ben, don't think I'm forgetting you. There is a question here from the audience, which rightly notes that water rights are really done at the state level. Is there anything that the federal government can or should be doing? They did a great job with that Colorado Water River Compact.
I thought you were going to say they've done a great job on sequestration so far. Yeah, there's some real basics here, and when you talk about law and policy and water, and one of them is that when it comes to water quantity, water allocation rights, the country has embraced the principle that that's a state-level decision rather than a federal decision, unless you're talking about certain compacts, interstate matters that do truly transcend the state water law.
But should the feds get more involved given this energy-water nexus that's developing? Or
yes, but not in the sense of allocating rights at the state level, the state legal systems. I would say this, there is a tremendous need for federal leadership on water. I truly believe, I disagree with people who want to end the debate on the role of the federal government simply by saying all water is local and that's it. We're talking research, we're talking innovation at ARPA-E here. 3 of the largest national water and wastewater trade associations and research foundations have come out with a roadmap on the utility of the future. And one of their specific recommendations is there needs to be an ARPA-W for water innovative, leading edge research on water. And I would say at the federal level, as opposed to allocation of state-based water rights, there's an amazing and embarrassing amount of low-hanging fruit when it comes to research on monitoring of water quantity and quality and trends. That continues to be a huge gap compared to the Clean Air Act, the drinking water and wastewater laws in the country. There's a real need to understand, particularly in the context of climate change, which really is water change. So I think a really important role there for the federal government. And then I unabashedly would say there are federal environmental laws that need to continue to have national standards that makes the country strong and envied by other countries around the world when it comes to clean and safe water. It's just they have to work extra hard to not be dictating specific technologies or to step over the states, who increasingly, if they have sufficient funding, the states are in as good a position to carry out various water laws and authorities. So there is an important role for the feds when it comes to water.
Please.
If I could add one note from our perspective, Department of Energy granted us money to start the water recovery project, which gave us the prototype, which is now commercial, which they ran that out of the fossil fuels office. We're very appreciative of it. This technology would not exist without that, but is now commercial. So there's certainly, I think, a role to play in seeding steps forward in a fairly conservative market, because we tried to work with utilities to do that on some kind of basis earlier, and that's a pretty tough sell. So,
ARPA's for everybody. So a couple more general questions that came in that I encourage you all to kind of jump in on. This one from someone in the audience. What about distributed water treatment or distributed desalination, is there a role for kind of smaller scale water technologies and energy technologies that use water?
Yeah, I think that the reality of distributed desalination is in fact the case in the U.S. I think there's something like 40,000 reverse osmosis units operating in the U.S. at much smaller scale. So the scale of about, say 1 million gallons a day versus 50 million gallons a day. It's being used a lot in industry, a lot, for instance, in I think cleaning water that comes from the fracking process in the energy industry. So it's there. It advances the state of the art, particularly in membrane technology and all. And so that's the status quo. I think the innovation is to take that and do it at a utility scale, in a way that has a meaningful impact on the water supply of an area.
Can I just add really fast that we're talking about paradigm shifts and transformational moves that on the water treatment side of the equation. There absolutely is a growing movement to be thinking about on-site, decentralized, distributed systems. We all know septic systems for years have been relied on. The country, national water policy for the U.S., took great pride in moving towards centralized treatment for wastewater in the 50s and 60s and 70s, and that's been a tremendous success story. And they have these systems, 16,000 publicly owned centralized treatment systems around the U.S., which are aging. And now there really is a greater emphasis in technology availability for more decentralized systems that can work better. I saw a really big interest in that right after 9/11. I was at EPA, and Homeland Security folks were also jumping on that bandwagon. I wouldn't say it's a bandwagon, but it's definitely there is an increasing role, and agencies and entrepreneurs are taking it seriously because it can make some sense. I'm waiting for my app so that I can treat my own wastewater at home. But I do think that is one of those new trends that will grow stronger.
I don't think they're going to build that into the iPhone.
No?
I don't see it.
One note in going to plants, a lot of power plants as I do, the chemist is a really important person at every plant. Number one. Number two, most of them are running some sort of water treatment or water remediation operation essentially on site. And it's exacerbated even further as you get to the oil sands. One of the fellows there characterized it as a water plant with oil as a byproduct. Yeah. You're really pulling up 3 barrels of water for every barrel of oil that you get out of the place. And so the 80% of the equipment on site was really water treatment, water separation type equipment. So it's very, very distributed at this point, and a lot of it's reverse osmosis and a lot of those type of technologies. So.
All right, so we have about 4 minutes left before we get that summit wrap-up. So I want to leave it with the biggest question that came in over the interweb, which is, what if we get it wrong? What's at stake? Are we going to, run out of food, electricity, government bureaucracy, and I don't know what would have? Well, desalinization is the answer. What's at stake if we get this wrong? You guys can do it. Jump in.
Life.
Yeah.
Or quality of life, I guess. It's life is maybe overly dramatic, but our increasing population is demanding increasingly more water to sustain a quality of life, whether that means, obviously beyond drinking and food, but it means better food and golf courses and all the rest of it. So we need more water, and we need to do ways to use it more efficiently. And get new supplies, or else it will, undermine the quality of life, in my view.
Mm-hmm.
I think from a power perspective, I'll pick up on what Ben said. Technology works, but not instantly. There are ways to continue to generate from a water perspective all the way to dry systems, although retrofitting a wet with a given turbine to dry is not very feasible. These hybrids are feasible. I also think it's incumbent on big users like power plants to do what they can to be as efficient as possible. It's much more difficult to control consumer use of water and these very diverse uses of water that people are demanding. So the big users, I think, have more responsibility.
So I was just waiting for this one because, there's actually some good archaeological evidence that
Science.
Yeah, cultures that really had sophisticated irrigation systems for their agriculture ended up, succumbing, and not all of that was necessarily due to drought, but it certainly had an impact on the demise of those, whether you're talking about the Egyptians or the Incas or even the Babylonians. I told you I'd get that one in.
They had a salt problem, too.
Exactly, because eventually through the irrigation they got salinity issues, and there is a lot at stake, and it has been a lot at stake all through history, and so I think how we balance that agricultural use, the industrial use, the consumer use, and then there's this other thing called the ecosystem, right? All of the things that we love and enjoy as well and want to have and get correct as we go through the process. So there's a lot at stake.
That is a great way to end this. I hope you will join me in giving a round of applause both to yourselves for attending and asking great questions, and also for my excellent panelists.
Great job, guys.